So, um, imagine walking up to an exclusive nightclub that you've been to 100 times. You know the staff, you know the layout. I mean, you are a regular.
Yeah, you practically live there.
Right. But tonight, before you even reach for the door handle, before you open your mouth to say hello, the bouncer just takes one look at your shoes and permanently bans you from the premises.
Oh, wow. Just instantly.
Instantly. No explanation, no argument, just a slam door. And that sudden, seemingly irrational rejection is exactly what happened to a developer named Ang. Digitally speaking, of course.
Right.
When they tried to run a really simple piece of software. Welcome to our deep dive. I am so glad you're joining us today.
Yeah, and honestly, that feeling of staring at a locked door with a shifting keyhole is what makes this specific incident so fascinating to dig into. We're looking at a source from May 7th, 2026.
Yep, part 129 of a developer blog.
Exactly. It's titled Notes on Haskell Programming by a developer named Ang.
Which is going to be our main mission for this deep dive. We're taking a highly technical roadblock specifically, a TLS handshake failure in a tool called Hoogle, and using it as a magnifying glass.
It really is a great case study.
It is. We want to understand the hidden security mechanisms and, frankly, the fragile interconnectedness of the modern internet. And I want to promise you right now, even if you have never written a single line of Haskell code in your life, you need to stick with us.
Oh, absolutely. The code is just the setting for the story.
Exactly. The themes we're exploring today, like the pain of troubleshooting phantom errors, the total illusion of the quick fix, and the invisible security shields protecting your data every millisecond. I mean, those are universally relatable for anyone who relies on modern technology.
Okay, let's unpack this. Set the scene for us. What was Ang actually trying to do before this digital bouncer slammed the door?
Well, it starts with a really standard, almost mundane developer task. So Ang was working on a personal project using Haskell. Now, Haskell is a very strict, mathematically oriented programming language, right?
And the ecosystem for it relies heavily on a tool called Hoogle. Think of Hoogle as a highly specialized local search engine just for Haskell developers.
A local search engine, like it runs directly on your machine.
Yeah, exactly. Instead of just searching for the name of a function on the web, it actually lets you search by the type of data you're trying to manipulate. So you tell Hoogle what kind of puzzle piece you have and what kind of shape you need to output.
Oh, that's clever.
It is. And then it finds the exact piece of code from the vast library of Haskell packages that fits that exact shape.
So, I mean, it's an indispensable tool. You really can't build much without it.
Basically, yeah. You need it.
So Ang is just trying to get their tools set up for the day. And they run a very simple command in their terminal. It's just Hoogle generate.
Right, which just tells it to build those local databases on their machine so they can start searching.
But it crashes hard. And this is where the universal frustration of software really shines through. Because Ang notes in the blog that they didn't just give up. They tried multiple versions of the tool.
The classic developer troubleshooting steps.
Exactly. They used the rock-solid stable version from their package manager. I think it was version 0.5, 0.1, 8.4. Still crashed.
Yep.
Then they thought, well, maybe it's a known bug, right? So they pulled the absolute bleeding edge, latest version, straight from the GitHub repository. Version 0.5, 0.19.0, identical crash.
Which is a massive red flag in troubleshooting. I mean, when multiple vastly different versions of a software tool fail in the exact same way at the exact same moment, you can rule out a localized bug.
It's not a typo in the code.
Exactly. This is an environmental issue. Something fundamental about how Hoogle is attempting to communicate with the outside world is just failing.
And the error output that Ang's terminal spits out is just a terrifying wall of jargon. Ang's machine is trying to download a master list, a file called cabal.config.
Right, from a server hosted at www.stackage.org over port 443.
And suddenly the console just vomits out an HTTP exception request drop.
Oh, man.
Yeah, and this cascades downward into an internal exception, which finally triggers a handshake failed error.
It's enough to make you want to close your laptop and just, rethink your career choices.
Seriously. I would be looking up farming real estate.
But buried at the very bottom of that cascade, within that huge wall of text, the application reports one vital clue. It says, and I'm quoting here, expecting server. Hello, got alert. Alert level fatal, decode error.
See, I'm going to push back on that being a helpful clue at all.
Really? What?
Like, if I am Ang and I'm looking at my screen and I read the words decode error, my brain immediately goes to file corruption.
I see what you mean.
Right, it sounds like a typo.
Yeah.
It sounds like Hoogle successfully downloaded the cabal.config file, tried to read the text inside it, and the formatting was scrambled. It sounds like a broken file format, not some massive, fatal network security lockdown.
The terminology is definitely misleading if you aren't deep into network protocols. In this specific context, decode error isn't about reading a file at all.
So what is it?
It's the network's equivalent of a generic rejection stamp. It's masking a much deeper structural refusal from the server. And to really understand why the server threw that specific error, we have to look at how Ang initially tried to fix it.
Right, so Ang sees this network error, assumes the server is just being, overly sensitive, and thinks, okay, the network is throwing a fit, let's just tell it to relax.
Exactly.
Which brings us to the attempted quick fix, the insecure flag. Ang goes back to the terminal and runs the command again, but adds the bypass. They type Hoogle generate insecure.
The universal developer workaround. I mean, if the strict security protocols are getting in the way of downloading a simple text file, just tell the application to bypass the security protocols entirely.
But the error stayed exactly the same.
Yep.
The insecure flag did absolutely nothing. It was as if Ang hadn't even typed it into the command line.
Yeah.
And I honestly couldn't wrap my head around why telling a program to be insecure wouldn't force it to ignore a security error. That is, until we bring it back to that nightclub analogy we started with.
What's fascinating here is how well that analogy maps to the actual technology. Walk us through how you see it.
Okay, so imagine your computer is you, trying to get into this exclusive club. That's the server, stackage.org. The insecure flag is basically you deciding, you know what, I don't care if this club's safety inspector certificate is expired or totally fake. I am willing to take the personal risk, just let me in.
Right, you're waiving liability.
Exactly. But the error Ang is getting isn't happening when you check the club's safety certificate. It's happening during the initial handshake.
The very first interaction.
Right. It's like you're walking up to the bouncer, but you're wearing flip-flops, and the club has a strict, unwritten dress code. The bouncer rejects you at the curb. You get bounced at the door before you even have the physical opportunity to say, hey, I don't care about your safety certificate.
You don't even get to have the conversation.
Nope. The connection is violently terminated long before the certificate validation phase even begins.
And that bouncer analogy holds up perfectly because it illustrates the precise millisecond by millisecond timeline of a secure internet connection.
It's not just a single step, is it?
Not at all. When your computer connects to a server over port 443, which is the standard port for HTTPS, secure web traffic, it doesn't just instantly start downloading files. There is a very rigid protocol.
The handshake.
Right. First, the client and the server have to agree on how they are going to encrypt the data. That is the handshake. The client says hello, the server says hello back, and they negotiate the math.
And then what?
Well, only after they agree on the encryption method does the server hand over its ID badge, its security certificate, just to prove it is who it says it is.
And the insecure flag in Hoogle is specifically programmed for that later step. It literally means ignore an invalid ID badge.
Exactly. But because the negotiation over the encryption math failed instantly, the ID badge was never even pulled out of the server's pocket.
Oh, wow.
Yeah, so the flag was entirely useless because the step in the timeline where its job starts was never even reached.
Okay, so if the handshake is failing before certificates are even exchanged, what exactly is the server rejecting? Why is the bouncer taking one look at Hoogle's flip-flops and turning it away?
It comes down to ciphers.
Ciphers.
Right. A cipher is essentially the specific mathematical algorithm used to lock and unlock the data. Because there isn't just one way to encrypt the internet, there are dozens.
Okay, that makes sense.
So when Hoogle reaches out to the server for that initial client, hello, it sends a list. It says, hi, I'd like to connect. Here is a menu of all the encryption ciphers I currently know how to use. Pick your favorite one and we'll use that.
And Ang's investigation into the code revealed that the default TLS library that Hoogle was using under the hood, which was version 1.9.x, was bringing a menu that included some really old legacy ciphers alongside the modern strong ones.
Yes.
But modern content delivery networks, or CDNs, the massive server farms that actually host sites like stackage.org, they have quietly updated their global security requirements. They are locking things down and refusing to support older math.
They've drawn a hard line in the sand regarding what algorithms they consider safe.
But wait, here's where it gets really interesting to me. I need to understand the logic of the server here.
Okay, lay it out.
If the client offers a list of options, right? Let's say Hoogle walks up and offers a menu of 10 different ciphers.
Sure.
3 of them are old and weak, but 7 of them are modern, mathematically sound, and incredibly strong.
Right.
Why doesn't the CDN server just act like a reasonable bouncer and say, hey, I see you have some weak options on your menu, but I also see you have the strong ones we require. Let's just use one of the strong ones.
That would be the logical thing to do.
Right. So why throw a fatal decode error and terminate the entire session just because a weak cipher was merely included on the list of options?
That is the crucial mechanical question of this whole deep dive. The reason servers can no longer be reasonable is because of a vulnerability called a cipher downgrade attack.
A cipher downgrade attack. I am guessing that involves forcing the server to pick the worst option on the menu.
You are spot on. Imagine a malicious actor, a hacker, sitting between you and the server. Maybe you're on public Wi-Fi at a coffee shop, and they are intercepting your traffic in transit.
Okay.
Remember that the initial client hello, where you send your menu of supported ciphers, is sent in plain text. It has to be, because you haven't agreed on how to encrypt the conversation yet.
Oh, wow. Wait, really? So the menu itself is completely exposed?
Completely exposed. So the hacker intercepts your menu of 10 ciphers. They secretly cross off the 7 strong ones, and they forward the modified shortened list to the server containing only the 3 weak, outdated ones.
And the server's completely blind to this.
Totally blind.
It just looks at the list and says, well, I guess this particular user is on an ancient device that only supports weak encryption. I suppose I'll be accommodating and use one of those.
And just like that, the trap snaps shut. Your connection is established using a weak cipher that the hacker already knows how to break in real time.
That's terrifying. Right, you look at your screen and see the little padlock icon in your browser thinking you're secure. The server thinks it gracefully accommodated an older piece of software. But the hacker is sitting right in the middle, decrypting and reading absolutely everything you send.
That is a brilliant and totally invisible attack. So the only way for the modern internet to truly defend against a cipher downgrade attack is to adopt a policy of absolute zero tolerance.
Zero tolerance is the only defense. Modern servers are now configured to scan that initial menu, and if they see any weak cipher listed, even if strong ones are also present, they do not negotiate.
Hey, let's pull a plug.
Exactly. They don't try to pick the best option because they can no longer trust that the list hasn't been tampered with. They assume the connection is actively compromised or that the client software is fundamentally insecure, and they slam the door shut. They terminate the session instantly.
And that abrupt, violent termination by the CDN server is what trickles all the way down to Ang's terminal as a fatal decode error. The server essentially hung up the phone while Hoogle was still mid-sentence.
And because it hung up during the initial protocol negotiation, the network library on Ang's machine couldn't decode a proper response, hence the decode error.
Okay, so the mystery of the error is solved. We know exactly why the server is violently rejecting the connection. It's protecting us from downgrade attacks, but refusing to even look at a menu containing weak ciphers.
Which is a good thing for security.
Absolutely. So moving to the solution, it seems incredibly obvious, right? Ang just needs to update Hoogle's cipher menu. Stop offering the weak ones, just update the underlying TLS library from version 1.9.x to the modern 2.x.x version, which presumably has dropped those legacy ciphers by default.
The logic is perfectly sound. But as anyone who spends their days in software engineering knows, the obvious fix is rarely the easy one.
Always a catch.
Always. Ang hits a massive architectural roadblock called transitive dependencies.
Okay, I get the basic idea that dependencies are linked, that your code relies on someone else's code. But why does updating one single library completely break the others? It feels like updating the tires on your car shouldn't shatter the windshield.
Right.
Why is Ang trapped here?
Because these software ecosystems are more like a massive, intricate Jenga tower.
Oh boy.
Yeah. You can't just forcefully yank out a foundational block from 2018 and shove a 2026 block in its place without the whole structure collapsing. It comes down to hard-coded version expectations.
Okay, walk me through that.
Well, Hoogle relies on a network library to handle connections. That network library relies on the TLS library to handle the encryption.
And the catch is, the network library isn't just loosely asking for TLS. It is strictly programmed to expect the specific data structures and formatting of TLS version 1.9.
Yes. If Ang tries to force the ecosystem to use TLS version 2, the network library looks at the new code, doesn't recognize the shape of the data, panics, and outright refuses to compile.
It just gives up.
Exactly. Upgrading the one block you need to fix the cipher list threatens to topple the entire tower of dependencies that the Haskell ecosystem relies on. The ecosystem simply isn't ready to absorb that upgrade smoothly yet.
So Ang is trapped in this digital purgatory. The modern internet server won't accept the old 1.9 library because it's a security risk. But the local software ecosystem won't accept the new 2.0 library because of rigid transitive dependencies.
Caught between a rock and a hard place.
They really are. They're squeezed between an uncompromising security policy and an inflexible web of code. Which leads us to the climax of this whole ordeal, the manual patch. Aang realizes they have to perform a surgical strike on the open source code of Hoogle itself.
Right. If you can't replace the broken part with a new one, you have to open up the broken part and forcefully rewire how it behaves.
And reading Aang's blog, the exact code changes are fascinatingly precise. Let's break this down without getting lost in the jargon. Aang has to go into two specific files. The first one is the configuration. Right. First, Hoogle.cabal. This is essentially the master blueprint of the project, where Aang explicitly tells the system, hey, we're going to manually interact with the network TLS libraries. Then they open search input download.hs.
Which is the actual mechanism, the engine making the call to the internet.
And this is where the scalpel comes out. Aang imports a very specific function called ciphersuite strong, and that's from network.tls.extra.cipher.
And then they dive into the connection manager settings.
Right, the literal rulebook Hoogle uses before talking to the internet. The function is called CMK manager settings, and Aang explicitly configures it to use TLS settings simple. Am I right in thinking they are essentially tearing out the old rulebook here?
That is exactly what they're doing. By manually injecting TLS settings simple and pairing it with ciphersuite strong, Aang is overriding the default behavior of the outdated 1.9 library.
They're hard-coding the dress code.
Exactly. They are taping in a strict, modern dress code for Hoogle to follow. They are forcing the application to walk up to the server's bouncer and say, here is my menu, and I am only offering these mathematically verified strong ciphers. I have scrubbed the weak ones from my list entirely.
And what's brilliant is that Aang's manual patch still maps that original insecure flag to the setting that disables certificate validation. Setting disable certificate validation.
Yes.
But now, because they've manually fixed the cipher menu, the handshake actually succeeds. The server's bouncer accepts the strict dress code, lets Hoogle into the lobby, and then Hoogle is finally in a position to say, by the way, I'm ignoring the safety certificate today.
Right.
The flag finally works because the prerequisite step, the math negotiation, was resolved.
If we connect this to the bigger picture, the broader implications of this single blog post are staggering. This one tiny surgical patch perfectly illustrates the delicate, sometimes terrifying balance of maintaining modern open source software. Well, you have this massive, globally interconnected ecosystem. Security threats evolve rapidly, forcing massive CDN providers to implement hard, uncompromising stops, like instantly dropping support for weak ciphers to prevent downgrade attacks.
Right, they have to move fast. But the software ecosystems that developers rely on, the intricate Jenga towers of transitive dependencies, they move incredibly slowly. They require consensus and massive coordinated updates across the thousands of projects.
And when those two realities collide, the lightning speed of mandatory security updates and the heavy inertia of transitive dependencies, things just break silently.
It's a disaster waiting to happen.
It is, and it requires individual developers, like Aang, to dive into the plumbing and manually patch the leaks just to keep their basic tools functioning.
So what does this all mean for us? We started with a baffling, seemingly illogical decode error in a niche developer search tool.
We did.
We explored how a totally logical quick fix, the insecure flag, failed completely because it fundamentally misunderstood the rigid, step-by-step timeline of a secure handshake. We uncovered the invisible war happening in the background, modern servers forcefully hanging up on older tools to protect our encrypted data from cipher downgrade attacks.
Which is vital protection.
Very true. And finally, we saw the harsh reality of the software supply chain, how a tangled web of transitive dependencies can trap a developer, forcing them to manually hack their own tools to bridge the gap between outdated code and modern security rules.
It really is a remarkable journey. I mean, it takes you from a single frustrating line of error text straight down to the fundamental architecture of internet trust.
It really does.
It proves that in technology, absolutely nothing happens in isolation. A security policy updated on a massive CDN server halfway across the world can silently and instantly break a developer's local search tool in their living room.
Which leaves me with a thought that I can't quite shake, and it's something I want you, our listener, to really mull over today.
Okay, let's hear it.
If modern internet security requires this kind of rapid, uncompromising action, dropping legacy support instantly without warning to stop active downgrade attacks, but our massive software ecosystems are locked into older tools because of these rigid, fragile Jenga towers of transitive dependencies, Are we heading toward a digital breaking point?
Wow, it's the question that keeps security researchers awake at night, honestly.
Think about it. How much of the software you rely on every single day at your job, the smart devices in your home, the apps in your pocket, is just one single CDN security update away from completely breaking down? Just sitting there, quietly failing in the background, waiting for some unknown, unpaid open-source developer like Aang to manually patch the gap.
It's a sobering thought.
We'd like to think of our digital world as this robust, engineered, unshakable machine. But maybe it's less like an engine and more like a house of cards held together by the sheer willpower and late-night debugging of developers who refuse to let it fall.
Yeah, that's a powerful way to look at it.
Next time you get an error message on your screen that makes absolutely no sense, maybe don't assume you just made a typo. You might just be caught in the crossfire of an invisible security war. Thank you so much for joining us on this deep dive. We absolutely love untangling these digital mysteries with you.
We really do. Thanks for listening.
Until next time, keep questioning the errors, and remember, just because the keyhole changes shape doesn't mean the door can't be opened. Take care, everyone.